Today, I will talk to you about an online slider paradigm designed to look at oscillator flexibility when used in combination with the extrapolation task. We're interested in studying the flexibility of oscillators, a property that has been understudied. Imagine an oscillator at its endogenous rate trying to synchronize to a rhythm being played. The oscillator is flexible in that it can speed up and slow down to match the rate of the rhythm. Oscillator flexibility can be measured using the extrapolation task, where a series of isochronous context tones are played, followed by a silent gap before a final target tone. An oscillator will start at its endogenous rate and then synchronize to the rate of the rhythm. A flexible oscillator will be able to maintain the rate of the rhythm and extrapolate through the silent gap. An inflexible oscillator, on the contrary, will quickly decay back to its endogenous rate once the rhythm has stopped playing. This will result in a less accurate timing judgment of the target tone. The target timing judgment is typically collected using a binary paradigm, asking participants whether the target was on time or not. These studies are usually conducted in the laboratory. However, as our labs were closed during the pandemic, we had to be creative and come up with an alternative online paradigm. We married a classical timing paradigm, the extrapolation task, to a method of responding, which is a visual analog scale that has been used to estimate magnitude in psychophysics, especially in pain research and human factors such as ergonomics. With the same stimulus, participants rated the extent to which the target was early or late on a continuous slider, where extremely early was on the left and extremely late on the right. The default position is centered for each trial. To avoid participants developing strategies based on previous trials, no numerical feedback of slider rating was displayed. The continuous slider allows us to capture nuanced perceptual judgment corresponding to various target offsets, which de-emphasizes the reference point of on time. This improved resolution also reduces the number of trials per stimulus needed to obtain reliable data. We first designed a base experiment, modified based on a classic extrapolation study by Manning and Schutz. We had 13 context tones using the sound of a woodblock click. The tones were presented at an inter-onset interval of 500 milliseconds, meaning 2 clicks per second. The silent gap lasted 3 inter-onset intervals, followed by a target offset ranged from 30% of the IOI early to 30% of the IOI late. Here we aim to validate the slider paradigm against the conventional binary paradigm. A second experiment was designed to see how well the slider paradigm generalizes to a wider range of target offsets. Here we expanded the offset timing beyond half of the IOI in both directions. In the next experiment, we increased the gap length from 3 IOIs to 7 and 11. The task becomes more difficult as participants have to extrapolate through a longer silent gap. This manipulation allows us to see how sensitive the slider paradigm is in capturing the decay of individuals' oscillator rate. In experiment 4, we varied tempo by adding 400 and 600 millisecond IOIs into the mix. We wanted to see whether the slider paradigm could pick up on global temporal context effects that we know occur when tempo varies from trial to trial. The last experiment shortened the context length from 13 clicks to 9 and 5. This means that participants have less tones to learn from and to synchronize to within a single trial. All experiments were conducted online using Lime survey, with participants recruited on Prolific. They were asked to wear headphones and to avoid body movement and vocalization throughout the study. Here is our data from the base experiment. On the x-axis are the target offsets, and the y-axis corresponds to the slider, coded from negative 100 being extremely early to 100 being extremely late. You can see that when done correctly, the slider ratings should have a positive slope, meaning that earlier offsets were rated as earlier and later offsets as later. To validate the slider measures against the conventional binary measures, we recoded slider ratings into a different dependent variable that is binary. All positive responses on the slider, which were rated as late, were coded as 1. The rest were coded as 0. Here is an example from one participant. We plotted how many trials out of all trials at the same offset were perceived correctly, and then fitted a sigmoid curve. As we know from psychophysics, the slope is a measure of sensitivity. A steeper slope suggests that the participant is better able to tell different target offsets apart. The intercept is a measure of bias. Here, it translates to where on the slider the participants centered their ratings around, which is often slightly shifted from the actual center of the slider. Similarly, for the slider coding, we fitted a straight line through the mean ratings and obtained a slope and an intercept. However, because different participants used a different range of the slider, we need to standardize the slope for the measure to be comparable across participants. So we transformed the slope to z-score using a permutation approach, which I will not go into detail right now, but I'm happy to explain during the Q&A. The z-transformed slider slope correlated with the slope from binary coding, and the two intercepts also correlated. Thus, we propose to use the standardized slider slope and the slider intercept for data analysis. Moving on to experiment 2. Slider ratings overlapped with the base experiment and linearly extended in both directions for expanded target offsets. It seems that the slider ratings were roughly proportional to the target offsets, suggesting that participants mentally mapped one IOI to each half of the slider. In the next experiment, where gap length was manipulated, we see that the slope of the red and purple lines are less steep than the green one, which is the base condition. What it says is that as the gap length increased, participants became less able to tell different target offsets apart. In experiment 4, we manipulated tempo. The three conditions do not seem to differ in slope. However, the purple line, which is the slower condition, shifted towards the later end of the slider. What it suggests is that there is a global effect of tempo. Compared to the base condition, the 600 millisecond condition had an overall atmosphere that was slower, which makes it feel like all target tones were late. In the last experiment, we manipulated context length. However, context length did not matter in terms of slope or intercept. This makes sense because the entire experiment was carried at the 500 millisecond IOI. Throughout trials, participants already learned the external dynamic well enough that a few less clicks in a single trial did not make any difference. To sum up, in studying oscillator flexibility, we adapted the slider paradigm for the extrapolation task. We showed that slider measures of sensitivity and bias are comparable to the binary measures. The slider paradigm generalizes to a wider range of target offsets and is sensitive to manipulation of stimuli parameters. In addition, the slider paradigm is efficient in that it saves time and trials. Each one of our experiments lasted an hour in average, with 10 trials per stimulus. It works well as an online paradigm. The efficiency also makes the paradigm practical for populations such as epileptic patients and children. In addition, the continuous data allows for application of various statistical analyses and models. All of these benefits make the slider paradigm a promising tool that advances our understanding of oscillator flexibility and other topics related to time perception. We'd like to thank Salim Bialik for making most of these studies on Lime survey and other members of our research group for feedback and support. And thank you all for listening.